All right. So again, this is a high-level look at thermal cameras and their use in the industry. It should not be mistaken for a high, the kind of the certifications that many people have undergone in this type of, you know, use of this kind of technology. But today we're going to look at the just high level thermal cameras. They are, hopefully many of us are familiar with infrared thermometers. We really don't discuss that in this particular one, other than you should have those if you are a technician or a surveyor, and likely that you do. They are a good low-cost way to find out temperatures of certain things. Uh, uh, Going on, though, we'll also discuss what you need to know before you use an infrared camera. I've already described how many people consider them point and shoot devices, and they're clearly not that. And hopefully the information I cover will show that. And to emphasize that these are best used if you take the time and become skilled at the use of thermal cameras. It is easy to create a colorful picture. It is not necessarily easy to create the kind of image you need for the analysis you need to do to help uncover some potential defects and other things that we'll see out in the field. All right, I'll keep this slide to a minimum. Again, just the idea is you want to be able to we want you to spark your desire to learn more about this. These are great devices and can be helpful out in the field, but you really want to make sure that you undergo the right kind of certifications necessary. And then lastly, this is my last CYA slide for the day, but remember, these are diagnostic tools. So if you're a surveyor listening in, just like a moisture meter or any sort of testing you might do, it's a tool that is to be interpreted. Oftentimes we will hear language such as, thermal imaging discovered moisture in the deck or whatever it happens to be. And hopefully all of us here understand that it gives us data that helps us interpret possible conclusions, but, it doesn't specifically, tell you that there's water or whatever. So you need to be able to do the analysis. And likewise, the language we use with clients, then it is very important that that we can get ourselves into certain liability problems if we state our conclusions very succinctly when they could be more broadly interpreted. All right, so starting with the end in mind, so I start with kind of my conclusion slide a little bit. Thermal imaging and thermal cameras are a great way to see beyond your normal senses. I remember I've been in the industry many, many years, and I remember back early in my career trying to work on a windlass problem, and ran the windlass for a while, and then stuck my hands where the cables are connected just to see if they were loose or anything like that. And of course, had a loose connection that built up a lot of heat. And learned a very powerful lesson about just how hot those connections can be. But thermal imaging gives you another possibility if you're a technician looking at a similar circumstance, that you would likely to see that reflected on the screen and not in a very serious burn. Again, I mentioned low prices really have had led to the conclusion on many people who have not gone through training that these are very simple point shoot devices. They are easy to turn on and get color for screens, but you do really need to know what you're looking at so that you can interpret it easily. And some of the slides we'll talk about moving forward, we'll talk about the theory of it, so that you can deploy that. If you're new to thermal imaging, you can sort of know what you're looking at so that you can get more out of the tool. Last bullet point, just to confirm, these do offer up the temperature, actual readings of things, but the real power in this kind of tool is to look at comparisons. You're looking for really the delta T, or the differences in temperatures And then based on that and based on your knowledge of what you're looking at, you should be then able to, draw some conclusions based on that. But to look at a thermal image and have the difference between 90 versus 92 degrees as just an example, the actual quantification of temperature is less important than how we use it as a comparative tool. So both, and this is the only slide that I'll have any sort of infrared thermometer or anything on it, but both of these do detect electromagnetic waves, and I'll talk a little bit about the theory in a minute. The difference, of course, is that these have the sensors in thermal cameras have the ability to take a landscape of temperatures and be able to reflect whatever's in its field of view more accurately than a simple infrared gun where it's more of a spot or kind of a cone of temperature that it's looking at. Generally speaking, we're pretty agnostic about brands and all that stuff when we talk about infrared cameras. There are a lot of solutions. And so I don't talk a lot about that in this presentation, other than to say, in general, the more resolution, the better. If you are a technician or just looking for things like electrical, looking for hot spots, loose connectors or corroded conductors, things of that sort, then there are offerings out there that are fairly, low resolution in terms of the pixel resolution of the camera. But in general, more is better. And also, you will find cameras that will offer a variety of temperature capabilities. Lower units typically are maybe max out at 488, I think, in terms of the thermal resolution, and higher quality ones will go above 1,000 degrees. But again, we're not selling cameras in this particular presentation, just to give you an offering of what you might be looking at. Of course, price is the trade-off for resolution, so you have to be budget-minded in terms of how you want to tackle that. So high level, what is infrared thermography? They're basically these devices that will detect the heat of objects based on the infrared radiation they emit. Technically, I mentioned in the previous slide, it's electromagnetic radiation, but we'll see in a moment how that translates to temperature. But what we know is that all matter that is above absolute zero will transmit or emit thermal energy. I won't have too many. This kind of reminds me a little bit of junior high science, but just as a quick reminder, the light that we can see as humans is really quite narrow in the wide spectrum. And over to the right in this diagram, you can see the infrared band. And it's in that band that these cameras operate. They operate, depending on the camera, in a variety of parts of that spectrum. The number 3, I won't go through all of this for you, but number 3 is really the range of the cameras that we deal with. And they're really dealt with in things like structures, housing, inspections and things of that sort. You're looking out at the long wave end of infrared, which runs, I think the FLIR cameras are about 7,500 to 14,000. So again, these all operate more in the long wave infrared part. Some of the gas industry and some other things have more refined equipment that look at different parts of the spectrum. All right, we'll continue. Before we looked at some of the pictures, again, the idea here is someone who is knowledgeable about using these types of devices need to understand a little bit of the theory behind it so that they can interpret what the various colors and temperature indicators are on the camera. High level, and this goes back to sort of thermodynamics, right? Heat flows from hot to cold. So just keep that in the back of your mind. I bring that up because oftentimes in an image you will see how that heat is being transferred through the image that you see. That heat basically is transmitted one of three ways: through convection, through conduction, and through radiation. Convection really talks about the heat, the movement of heat through some sort of gas, for example, the air we breathe, right? So in heating in our house, for example, um, heat rises, cool air comes to take its place, all that type of stuff. That's really a convection is that we're talking about in that particular case. There is conduction. So when we talk about conducting heat, we're talking about the direct physical contact. Again, one of the key principles that you need to know or think about when using these devices is that that basically the greater the temperature difference, the greater the more easily you will see the gradients or the differences. In general, that the heat transfers to cold when the temperature is greater, it transfers more quickly. So as the temperatures become closer to one another, you get less of that transfer, and as you also get though less data for your thermal camera to be able to interpret. Then there's radiation. That's heat that's transmitted, again, as I mentioned, through an electromagnetic wave, through primary infrared, visible, and ultraviolet. But infrared, of course, is what we're really talking about when we talk about these types of cameras. To talk a little bit more of that, and when you start to understand and expand your skills in thermal cameras, there are, oh, wait a minute. Yeah. Let me back up just a minute. So I mentioned at the end of that, talking about radiation, just some more on that. And again, all of this is kind of the theory of it, but this all plays a big role when you start to use these types of cameras. Radiation, it is emitted from something. Again, as I mentioned earlier, all matter that is above absolute zero will emit some level of radiation. That is then propagated, and one of the unique characteristics about radiation is that can be propagated through a vacuum. Obviously, that's how we get heat from the sun, as an example. It can also, though, go through in certain transparent media, and I'll talk more about that, I think, as I go forward. And then that energy is absorbed. And if you look at and again, I'm not trying to read all these bullet points to you. I'm trying to paraphrase it for you. But if you read that bullet point, you'd see they can be absorbed. That increases the thermal energy of the absorbing rate. And that term "can" is pretty important because what we'll find when we talk about using these cameras in the field is some materials will absorb those better than others. And that will impact how you look at, interpret the data that you see on the cameras. When I have mentioned in previous, and in fact, this slide about electromagnetic waves, and we'll save the science for, we won't talk much more about the science, but just know that heat transfer is proportional to that. And that's how that these devices can detect the electromagnetic wave and be able to convert that into thermal information, thermal data. All right. As you start to learn and talk more and use these types of devices, there are really three important concepts that you should think through when you're using a camera. The first is that the idea of transmittance, and that is the proportion of the radiation that passes through a material. That will vary greatly depending on the material that you're trying to capture an image of. It is a misconception that thermal cameras can see through walls. They simply can't. And so when we look at, maybe on movies where you see they look thermal cameras and they can see, the bad guy on the other side of the wall or whatever. That's really not how it happens. Similarly, thermal cameras can't see through a standard window. There are certain types of windows that are made for that they can see through better, but a standard window actually appears opaque to a thermal camera. What you see, though, or what you may see if you're capturing an image through a window, is some sort of surface temperature change that is brought through by those major ways we transfer heat: convection, conduction, and radiation. But typically, and I'll see here, reflectance, one of the key concepts. Um, you can see the picture on the screen here is not is the reflection of the camera taker here, looking through, in this case, just a simple shower door. But you can see how someone who is not familiar with how these work may inaccurately think that the glass is a different temperature, when this is a radiation that's just simply being reflected. Emittance, another important concept that you will deal a lot with if you or when you use some sort of thermal imaging camera. Emittance and emissivity a lot of times is what you will see in the documents and on any sort of camera adjustments that you can, in terms of settings changes that you can make. Emittance basically is an efficiency number. So it reflects the ability of the material to emit the energy that it has. There are some materials that are better at doing that than other. A perfect emitter, something that can emit the exact amount of radiation that it has, is often, when you read about this or learn through other certifications, they'll refer to that as a black body. And so the emissivity in that case is 1.0, so it's a perfect emitter. As we use these type of the equipment out in the field, either as surveyors or as technicians, we have to be mindful of the image that we're capturing and what type of material it may be. So again, nothing really in the practical world is a 1.0. Painted objects, though, like flat black paint, can be somewhere in the 0.8 to 0.98 range in terms of emissivity. Something that we see a lot in the marine field, of course, is stainless steel. And if you look at the numbers there, you can see it's a very, very low number. So in fact, all types of metals, and in fact, the shinier the metal, the worse it gets, are very, very poor and have very, very low emissivity numbers. This matters because it can, to someone who is not aware of that, it can look things can look abnormally cold when they look at a particular image on the screen. So again, it's really important to understand what you're looking at when you're taking that. Just for your information, human skin, to give you a nice is about 0.96. That is one reason why infrared, thermometers for health work well, is it is a fairly good in terms of the emissivity that it projects. Here, before I go on with the bullets here, here's a great example. And these are fuses, and you can see an AGC fuse if you're depending on your knowledge of this sort of thing. And essentially, you can see that these bands, which are the metal, the chromed metal bands, appear very, very dark and cold. In real life, so to speak, this number would be very, very close in terms of temperature. If we were to take a thermocouple or something, would be very close in temperature to its surroundings. But the thermal camera doesn't see that, again, as a result of low emissivity. in general, and I've got some helpful tips a little bit later, but in general, the goal as you use these, now these cameras, you can change the emissivity setting if the larger field of view is a shiny, like a shiny metal as an example, or a poor, uh, low on the emissivity scale. Um, but the goal as a thermographer, someone taking the picture, the goal really should be to find areas that are higher on the emissivity scale rather than change the settings. Sometimes you have to change the settings, and oftentimes you have to, and that is certainly okay. But again, in terms of a goal, you're trying to take the raw image as close as you can to something that is closer to a black body than anything else.